This video is going to be covering our third and final form for graphing quadratic functions, and that is called intercept form. It's called intercept form because by analyzing the different parts of the equation, we can find the x-intercepts. I want you to write down the general equation for intercept form, and that would be f of x equals a times x minus p times x minus q. Starting with the first example, I gave you an equation and a graph, and we're going to use this to answer the questions over to the right. I want to start off by taking a look at the equation. So the equation is negative x minus 2 times x plus 4. So that negative out front represents the a value. When there's not a number written there, it's understood to be 1. So a is negative 1. Next we have x minus p. So here in the equation I have x minus 2. We are subtracting a positive 2, so p is a positive 2. Okay. X minus q, if I look at the equation, there's x plus 4. So we actually have to subtract a negative number in order to get that positive, meaning q is a negative 4. The first question asks, where does this graph cross the x-axis and how does that relate to the function? Well, if I take a look at the graph, I can see that there's an x-intercept at negative 4, and there's also an x-intercept at 2. How does that relate to the function? Well, 2 and 4 were the p and q values. So what I want you to write here is that p and q represent x-intercepts. Next, it says, where is the vertex in relation to the intercepts? So the vertex, remember, is the max or the min. I have a maximum at negative 1, 9 for this specific graph. Remember, the axis of symmetry will always pass through the vertex. So the axis of symmetry here is located at x equals negative 1. And it turns out that the axis of symmetry in the vertex will be exactly halfway between the x-intercepts. See how my axis of symmetry is at negative 1 and I move right 3 to get to the negative 4, or excuse me, left 3 to get to the negative 4, and right 3 to get to the positive 2. So what I want you to put here is that it is halfway between. It turns out if we ever wanted to find the x value of the vertex, so I'll say x value of vertex, which also happens to be the axis of symmetry, we can either look at the graph and count exactly halfway between, or we can find the average. So that would be p plus q divided by 2. Okay, we have some key information about graphing and intercept form here and here. So we're going to keep that in mind, but move on to the next example. Okay, it says the following is the graph of the equation y equals 1/2 times x minus 6 times x minus 4. Before I even look at anything else, I want to identify what a, p, and q would be. So a is 1/2 because that's a number out front. P is a positive 6 and q is a positive 4. Again, that's because of the x minus p, x minus q. in the general equation. Okay, using this equation and the graph, let's answer these questions. The first one says, why does this graph seem wider than the first one? Keep in mind, when we're actually changing the shape of the graph, that would be either a stretch or a compression. So now we need to remember which one would make the graph appear to be wider. Or you could just look at the A value. In this case, A is between 0 and 1, which should indicate to you that it is a compression. If A was greater than 1, it would have been a stretch, or it would have become more narrow. Okay. What is the domain and range of this function? You know, I just thought of something before I do that. When you have a stretch or compression, if I just give you the graph, you can tell what the A value would be by seeing that it moves right 1 unit and either up or down a certain number. So in this case, from the vertex to get to the other point, I moved right 1 unit, but we can see it only moved up half a unit. Because it moved up, A was a positive, so moved up 1/2, because that's the amount that it's increased. So just something to remind you of, and we're going to see that a little bit more. But going back to domain and range, remember, for domain, each parabola has a domain of all real numbers. As it moves to the left and as it moves to the right, it will always be defined. So they're approaching positive and negative infinity. The range, however, is restricted, and it's restricted because there's either a maximum or a minimum value. In this graph, we have a minimum. Remember, range deals with the y values, and we must always write it down to up. Okay? So my lowest point on this graph appears to be at, let's see, 1, 2, 3, 4, 5, negative 1/2. So the lowest point of my graph has a y value of negative 1/2. So that's what I want to use, is negative 1/2. I need to use a bracket here because this point is included on my graph. It represents the minimum. As the function goes up, it's going to increase forever, meaning it's approaching positive infinity. This time I need to use a parenthesis because infinity is not included in the graph. Next one. This time I just gave you the graph. And using this, we're going to have to answer these questions over here. The first one says, try to write the equation for this graph. How do you know what numbers and signs go where? If we think about the general equation, f of x equals a times x minus p times x minus q. If I want to write this equation, all I have to do is identify what a, p, and q are. Remember, we found out in the first example that p and q are the x-intercepts. I'm going to write that p and q are the x-intercepts. Looking at this graph, I can see there's an x-intercept at -1 and also at +3. It doesn't matter which one you let be p and which one you let be q. I'll just do -1 for p and a +3 for q. So in my general equation, I can plug in p and q. I have x minus a -1 becomes +1, and x minus a positive 3 becomes the expression x minus 3. So now all I have to do is write what a would be. Remember, a can tell us a couple of different things. The first thing it tells us is if the parabola opens up or down. In this case, the parabola is opening up, which means a is going to be some positive number. If it were to open down, a would have been negative. To find the actual numerical value, I have to look at the pattern. So to look at the pattern, we use the vertex and a point. You could use a point that's 1 unit to the left or 1 unit to the right. I usually just stick with moving 1 unit to the right. So if I move 1 unit to the right, I want you to notice that to get from this point to this point, I have to move 2 units up. So that means, again, since I moved 1 unit to the right and up 2 units, a is going to be a positive 2. So I put a 2 here. That is our equation. We also have to write the domain and range. Once again, the domain of any parabola would be all real numbers. You can either use the symbol or interval notation. And the range has to be down to up. There is a minimum here, so the furthest down I can go is here. The vertex appears to be 1, -8. Because it's range, I know I need to use the -8. Range is the y values. So -8 comes first with a bracket because it is included on my graph. And then as the function moves up, it's going to increase forever, approaching positive infinity. On the next page, we're going to graph and state the domain and range for numbers 1 through 4. I want to point out that for number 1, the equation is not written in intercept form. It's written in standard form. So I talked before about how whenever I give you something in standard form, we could change it and write it into a different form. In order to write from this form, standard form, to intercept form, we have to do something called factoring. Now, you briefly did this in Algebra 1, but we're going to see it a lot more in depth after we take a look at graphing quadratic functions. So just so you know, if I were to rewrite this by graphing, and again, we'll go over this later, it would actually look like 2 times x minus 1 times x minus 3. Looking at this form, I can identify A, P, and Q. A is a positive 2. P would be a positive 1, and Q would be a positive 3. Now I want to identify all this information using A, P, and Q. So the first thing I want to know is, what are the x-intercepts? Well, the x-intercepts are P and Q, so that would be at 1 and 3. We could go ahead and plot that on our graph as well. Here's 1, here's 3. Next, I want to know where the axis of symmetry is. The axis of symmetry, if you recall from the front page, is located exactly halfway between. So I'm going to write halfway between. Looking at the graph, I can see between 1 and 3, the axis of symmetry would be located at 2. If it wasn't so easy to tell, what you could do is use the equation x equals p plus q divided by 2, again finding the average of the x-intercepts, and I'll just show you p, which was 1, plus q, which was 3, divided by 2, becomes 4 over 2, or 2, and that's what we had identified. The axis of symmetry will always pass through the vertex. So when I want to know what the vertex is, the x value will be